So, students, this is the second part of Chapter 7, Thermochemistry. And we continue to discuss energy associated with physical and chemical processes. And now we're going to learn about enthalpy. Enthalpy is a state function. So enthalpy is defined as the sum of the internal energy of the system and the product of pressure and volume. So represented by the capital letter H. So H equals to the sum of the internal energy of the system plus the product PV. We're not really interested in this equation. We're not going to use it. We are really focused on enthalpy changes delta H. This is what is important to us. And enthalpy changes are defined as the heat involved in a reaction at constant pressure. So for physical and chemical processes, as long as the pressure is constant, I can say that the enthalpy change delta H equals to the heat that has evolved or heat that has gone into the system. So remember that heat is directional. So we have to know how the system begins, how the system ends, and we'll have an idea if heat is coming out of or going into. You're probably noticing a subscript right here on the bottom of enthalpy. So this is read delta H Rxn delta H of the reaction. So Rxn is an abbreviation for reaction. Any textbook in chemistry uses this. The last bullet talks about how close, numerically speaking, delta H and delta E are. So they start to become separated for processes that use large quantity of gas. We don't need to get into this again. What we're really interested in is the enthalpy change. Endothermic and exothermic reactions. So last class we saw that Q is expressed as a function of mass, specific heat capacity of the substance, and the temperature change that the substance is going through. What we are going to connect with here is how delta T affects the sign of Q, which in turn affects the sign of delta H, because delta H for us equals Q, because all the processes that we deal with are at constant pressure. Okay, so scenario number one. So let's talk about a process on the bottom of the screen that is endothermic. For an endothermic process, the definition of an endothermic process is that the system is receiving from the surroundings energy. So the system acquires from the surrounding energy. The temperature of the system goes up because the system is receiving energy. So that means that initially the temperature is low, and after some time the final temperature is higher. The temperature goes up. So delta T is TF minus TI. If TF is bigger, then this delta T is positive. When delta T is positive, on the top of the screen, Q is going to be positive. Why? Because mass is always positive and specific heat capacity is always positive. Well, if Q is positive, then delta H is positive. Let's now look at an exothermic process, what is happening there. So we have the system, losing temperature to the surroundings. And the temperature of the system, therefore, drops. And that means that the system has an initial temperature that is actually higher than the final. But when I'm calculating delta T, again, I have to do TF minus TI. And so with TF being lower in this case scenario, delta T is negative. Looking at the top of the screen, if delta T is negative, with these two quantities always being positive, Q ends up being negative, and if Q is negative, delta H is also negative. So what is the connection? Endothermic processes that have delta H positive, exothermic processes have delta H negative. These two are examples associated with the two processes, exo and endo. I don't like the word reactions here. I prefer the word processes because processes is more generic. Processes, I can talk about physical or chemical. And so on the first bullet, we have chemical heat packs containing iron fillings, and the iron fillings are oxidized. And so the process of oxidation of a metal, we saw this before, the metal loses electron, the metal's oxidation number goes up. Well, specifically in this scenario, this is happening because iron is reacting with oxygen. So this is an oxidation, reduction reaction, redox reaction, but it's also combustion. And what do we know about combustion reactions? A combustion reaction, if my reaction is the system, a combustion reaction is going to donate heat to the surroundings. So this reaction is used as a heat pack because the reaction produces energy. We touch the heat pack, it feels hot to the touch because the reaction is producing heat. The second bullet, we have a chemical cold pack. So it's a different situation. It's not a chemical process, right? It's the dissolution of ammonium nitrate in water. So what happens? We have NH4, NO3, solid, and when we put water onto this solid, the solid breaks up into NH4 plus and NO3 minus. But this specific dissolution needs energy, so the energy goes here to the left side. Energy plus the solid makes the dissolution happen. Some solids dissolve endothermically, some others dissolve exothermically. So this dissolution is an endothermic dissolution. When you touch the pack that contains the ammonium nitrate in the water, it's going to feel cold to the touch because the reaction is attempting to take energy from your hands. So summarizing enthalpy, the value of delta H for a chemical reaction is the amount of heat absorbed or evolved. Absorbed by the system, evolved from the system. So absorbed endo, evolved exo. Under conditions of constant pressure. So for an endothermic process, delta H is positive. The heat is being absorbed by the system from the surroundings. And if you touch the system that contains the process, it's going to feel cold to the touch. An exothermic reaction, on the other hand, has a negative value of delta H. The system is giving off energy to the surroundings. And if you touch the system that contains the process that is going on, it's going to feel warm to the touch. So, looking at it from a different perspective, an exothermic reaction, we have the surroundings temperature increasing. So, Here's the system. And the system gives off energy to the surroundings. So the surroundings temperature is going to go up because the surroundings is receiving energy. And so this extra thermal energy comes from the conversion of some of the chemical potential energy in the reactants into kinetic energy in the form of heat. So we have energy is stored in bonds, converted to movement, converted to heat. So during the course of a reaction, bonds are broken and new bonds are formed. There is a give and take of energy that happens. The products of a reaction have less chemical potential energy than the reactants in this case scenario. If I draw an energy diagram for an exothermic reaction, we have reactants, products. So the products of the reaction have less chemical potential energy than the reactants. This difference here, from here to here, is a sigh of relief that the system is giving us. It's coming down the roller coaster, right? The system begins high in energy, but finally when the products are formed, there's a relief because lower potential energy is stability. So forming products that are low in energy is an indication of forming stable products. A similar approach to endothermic processes. In an endothermic process, the surroundings temperature is decreasing. So let's look at it. For an endothermic process, the system is receiving energy from the surroundings. So of course the temperature of the surroundings goes down because the surroundings is losing energy. So during the course of the process, bonds are broken, new bonds are made in a chemical reaction. This is true. The products of the reaction have more chemical potential energy than the reactants. So similar approach here on the bottom of the screen. I have reactants now going into products, and the products have higher potential energy than the reactants do. So to acquire this extra energy, some of the thermal energy of the surroundings is converted into chemical potential energy stored in the products. Let's look at this exercise. And you can pause the video, try to answer, and then check your answer after that. We have an endothermic reaction that occurs in a flask. What happens to the temperature of the flask? Well, I'm going to draw the flask a little thicker. If inside the flask we have an endothermic process, right? And what I have in the flask is my system. My system is undergoing an endothermic process. The system is drawing energy from the surroundings, right? So the system is pulling all this energy. So if I touch the flask, I know the flask is going to feel cold. What happens to the temperature of the flask itself, the glass that is in, holding my system? The glass is going to feel cold because the temperature of the glass is dropping. We now know or have a good idea of enthalpy is, what enthalpy is. The enthalpy of a system, delta H of the system, is often the enthalpy of the reaction. So system and reaction are one of the same because we choose the reaction as the system. The enthalpy of the reaction can be calculated in 3 different ways. We're going to use the stoichiometry of a reaction. So the idea to use stoichiometry here is to connect moles with energy. We are going to also use Hess's law. So it's another way of calculating enthalpy of the reaction. And the last way to do that is to use the standard enthalpies of formation. And those are called delta H, 0, F. The 0 is the standard part. The F is the formation part. So we read this as standard enthalpy of formation. So let's take a look at the stoichiometry part first. The enthalpy of a reaction is an extensive property, which means it depends on quantity. The way I like to refer to this is if a reaction is exothermic, for instance, like this one here. Yes, we see the delta H negative, we know it's exothermic. So each one of the number of moles in this balanced chemical equation is also connected to this number here, meaning for every 1 mole of propane gas, 2,044 kilojoules of energy will be produced. A negative enthalpy is meaning that the system is releasing that energy, producing that energy. So 1 mole of propane produces that much energy. We can also use oxygen. Then 5 moles of oxygen produces that much. Any one of these number of moles can be used as a proportionality relationship with energy. So if I have 6 moles of CO2 being produced, I know that the quantity of energy that is being produced is this number times 2. Why? Because 6 is 2 times 3. So the energy produced is 2 times the referential energy, which is 2,044 kilojoules. Let's look at an example of this. If we have a thermochemical equation of reactant A and product AA, we need 2 moles of reactant A to get to the product. And this reaction is exothermic, and it produces 51.0 joules of energy. Every time we have 2 moles of A transformed into AA, we have 51 joules released. What is the heat associated with the reaction of 6 moles of A? 6 moles of A is input. I begin my dimensional analysis with 6 moles of A. moles of A on the bottom. And since I want heat, that's my energy, I have to have joules on top, because joules is a unit of heat. I'm going to look at my equation for information, because this conversion factor here comes from the balanced chemical equation. I see 2 moles of A producing 51.0 joules. So the answer to this problem is 6 times 51, 6 times 51 divided by 2, which is negative 153 joules. The negative simply indicates that the energy is coming out of the system. The energy is being produced. The heat is being produced. The second way to look at enthalpy, calculate enthalpy, is using Hess's law. So Hess's law states the following. If a reaction can be expressed as a series of steps, and then the delta H of the reaction for the overall, the whole thing, is the sum of the heats of the reaction for each step. So looking at the picture that appears on the bottom, we are interested in finding this much. Well, to find this much, what we can do is we can take the first enthalpy and connect to the second. We may not know what the third process is, but we can use the first process and the second process to figure out the third. Example. The example is coming on the next slide. So we're going to use Hess's law the following way. We have to look at these 3 bullets here. These are manipulations of enthalpy that we have to know. Every time we multiply an equation by a factor, the enthalpy is being multiplied by the same factor. So if I have A plus B yielding 2C, if I multiply the whole equation by 3, then the enthalpy that we had at first, this delta H here, has to be multiplied by 3 to obtain the amount of energy of the second process, because enthalpy is extensive, as we saw before. The second bullet talks about if a chemical equation is reversed, then delta H of the reaction changes sign. Processes that are exo in one direction are endo in the opposite direction. That's why we have to reverse the sign. And so you're going from A to B. If your enthalpy is positive going from A to B, if you go from B to A, your enthalpy is going to be negative. That's what this bullet is saying. And the last one talks about a combination, right? So if a chemical equation can be expressed as the sum of a series of steps, then the delta H of the overall is the sum of these steps. So I may be aware of 2 processes that exist. I may be aware that A to B gives me a certain enthalpy. And the second process is B going to C, enthalpy number 2. What if I want to know the enthalpy of A going to C? I want this enthalpy here. What is this energy? And so I can actually sum what I have been given. I can sum A to B with B to C. So when I sum these equations, I get A plus B on the left, I get B plus C on the right, the B cancels out. I am left with the equation that I want. And what is the enthalpy of the equation that I want? The enthalpy of the one that I'm looking for, delta H, is delta H1 plus delta H2. That's what this bullet is talking about. So consider the following chemical equation of 2A plus B yielding C. The enthalpy is given to us. What is the enthalpy for the reaction of 2C yielding 4A plus 2B? So pause the video, try to solve it, and I'll show you the solution. So the reference is the 2A plus B yielding C. When we go to the second equation, to C, what do we notice? We notice that the C has switched places. C used to be a product and now it's a reactant. And we also notice that the whole second equation has been multiplied by 2. So from here to here, 2 things happened. We had the switch and we had the factor of times 2. So we need to combine these 2 things. When a reaction is switched, products and reactants are switched, what happens to the enthalpy? The enthalpy changes sign. So the enthalpy of the bottom equation has to be the negative of the first. But not just that. Since the second equation is 2 times the first, we have to change the sign and also multiply that result by 2. So the answer is negative 244 joules. The third way to calculate enthalpy is using the standard enthalpies of formation. And because we're using standard conditions, we need to understand what these conditions are before we move forward. So this slide is basically stating what is considered standard, is defining what is a standard condition for us. So the first bullet, the standard state, is the state of a material at a defined set of conditions. Pure gas at exactly 1 atm pressure, pure solid or liquid in its most stable form at exactly 1 atm pressure and temperature of interest, which is usually 25 degrees Celsius. So the standard state is seen as pressure equals 1 atm and temperature of 298 Kelvin, right? 25 degrees Celsius is the same thing as 298 Kelvin. If you forgot the relationship, Kelvin equals Celsius plus 273. That's how you convert from one to the other. So solids and liquids, gases, substances in a solution with a concentration of 1 molar. So this is basically saying that these are the most stable conditions for these substances. We analyze variations of enthalpy in those standard conditions. Second bullet, the standard enthalpy change delta H 0 is the enthalpy change when all the reactants and products are in their standard state. important definition. This is something that you need to know. The standard enthalpy of formation, delta H 0F, is the enthalpy change for the reaction forming 1 mole of a substance from its constituent elements. And the constituent elements have to be at their standard states. Another definition that you need to know. I'm going to be adding information to that slide concerning specific substances that you need to know. So the standard state of metals, if we consider the pressure of 1 atm and temperature of 298 Kelvin, right? How do we find metals? We find them as solids. In those conditions, metals are solids, right? So, examples, NaS, zinc, iron, and so on and so forth, right? Metals are, under those conditions, solid. Let's look at some other specific substances, say group 8A. Group 8A elements present themselves under those conditions as monoatomic gases. Group 8A are the noble gases, right? So examples, neon, xenon, and etc. There are some substances that present themselves as diatomic gases. So you already know this: hydrogen, nitrogen, oxygen, I forgot the G, fluorine, chlorine. For those elements, for the 5 elements that I have listed here, they are gases, yes, but diatomic. Bromine, liquid, diatomic. Iodine, solid, diatomic. Again, what I'm listing for you, and this is something that you need to know, is how specific substances are most stable under the conditions of 1 atm and 298 Kelvin. To complete this list, we're going to be adding carbon. Carbon is a solid under those conditions, but we have to list something else. The element carbon actually presents itself in nature in 3 different solids, but the most stable of these solids is graphite. So you have to say solid, comma, graphite in parentheses. Phosphorus presents itself under those conditions as before. Solid, red. Sulfur, S8, solid, rhombic. How exactly do you use this information that I'm giving you? Say I ask you to write the equation for the formation of ammonia. So this is very specific. We have to remember the definition, right? So a few minutes ago we were looking at delta H 0F. And this is the enthalpy under standard conditions of the formation of a substance. And this substance is at its standard state, and its constituents are also in their standard states. So when we write this equation for the formation of ammonia, we have to keep in mind the definition, okay? I'm going to begin with the arrow, and I have to, it's a must, I have to have 1 mole of the product here. Ammonia is a gas, so I begin like this. Since I want the formation of ammonia, I will write, I'm producing 1 mole of ammonia. The next step is to think about the constituent elements. What are the elements that form ammonia? Well, it's nitrogen and it's hydrogen. Those 2 elements. Okay. Then I have to ask myself, what is the most comfortable way these elements present themselves in nature? What is the standard state? Right? Which state are they most stable? They're both diatomic, and they're both gases. This is how we write it. And so it's nitrogen plus hydrogen yielding ammonia. Okay, but the equation is not balanced. And we are bound by this number 1. We cannot touch, we cannot change that number 1, which forces the left side of the equation to have sometimes fractions. So let's think about it. The right side of the equation has 1 nitrogen atom. I need to have 1 nitrogen atom on the left side. So I need half of 2 to obtain 1. The right side of the equation requires 3 atoms of hydrogen. On the left side, I have 2. So to end up with 3, I need a 3 halves. I need 3 halves of 2. 3 halves of 2 gives me 3. I can add to this problem, and besides ammonia, I can ask you to work on calcium carbonate. So I'm going to do this again. Begin with arrow. 1 mole of calcium carbonate, which is a solid. I'm going to list on the left side the elements that make up calcium carbonate. They are calcium, they are carbon, and they are oxygen. I'm listing each element. Asking myself, what is the most stable state for each one of them? Calcium is a metal, so I'm going to write a solid. Plus carbon. Okay, carbon is solid graphite plus oxygen, gas, and diatomic. Now we balance this equation. Again, keep in mind that we don't touch the number 1. So we need 1 calcium, left side, 1 calcium. We need 1 carbon, left side, 1 carbon. And we need 3 oxygen atoms. We have to have 3 halves, again, 3 halves of 2 to end up with 3. We're going to use the standard enthalpies of formation from a table. a table will be given to you, or the values will be given to you. And so you take these standard enthalpies of formation from the table, from the problem that I give you, whatever, and you'll be able to calculate the enthalpy of the reaction, putting everything together. Now, the table that we have here is small. It is just an excerpt. These enthalpies of formation, the tables are monumentally large because it's data collected over a lot of substances. The table is alphabetized, so you notice that the presentation of the information is in alphabetical order, which makes it easier to find it. So we're going to look now at the formation reactions. So it's basically what I was showing in those examples with a little bit more detail. So these are reactions of elements in their standard states to form 1 mole of a pure compound. If you're not sure what the standard state of an element is, find the form in Appendix 2B that has delta H 0F equals 0. Well, I created a list for you of what you need to know. So if you memorize that list, you're going to be able to write everything that I ask of you. The last bullet, because the definition requires 1 mole of the compound to be made, the coefficients of the reactants may be fractions. We have already seen this. We're going to take these standard enthalpies of formation and we're going to use in this equation that appears in boldface. Any reaction, first bullet, can be written as the sum of the formation of reactions or the reverse of formation of reactions for the reactants and products. The delta H0 or is standard enthalpy for the reaction is then the sum of the delta H0F for the component reactions. These 2 bullets are complicating things tremendously here. Okay, so let me try to simplify it for you. Enthalpy is a state function. And I talked to you about state function when I showed you that picture of the mountain and the climbers, right? You had, don't laugh at my little climbers, we had the climbers on the steep path, and we also have those zigzagging on their way up, right? And I mentioned then to you that they all begin at the base of the mountain. They all end at the top of the mountain. Because the thought process here is that only final and initial conditions are important. When we have a chemical process, we begin with the reactants and we end with the products. So reactants is initial condition and products are final condition. So if you look at the equation in boldface, what do we have? We have information about products, which means final condition, minus information about reactants, which means initial condition. So basically, this equation is saying that the delta is whatever I am trying to figure out of final minus initial. That's a very simple approach of this equation. I'm going to dissect it a little bit more, but in a nutshell, this is what we're doing. We're doing final minus initial. What is exactly we have to pay attention to? We have to pay attention to the symbols and to the variables, right? So let's dissect that. This is the letter sigma. And sigma represents summation of multiple terms. So if I have multiple products, if I have multiple reactants, a condensed way to write the equation is to use the summation. N represents the number of moles. And delta H0F comes from the tables that we saw before. We extract these values from the table and substitute in this equation. Let's say we're interested in calculating how much energy is produced. How do I know it's being produced? Because it's combustion, right? It's a combustion reaction. It's a reaction with oxygen. So I know that energy is going to come out here. Energy is going to be produced. I know that when all is said and done, delta H is going to be a negative number. I'm predicting that. So one way to tackle this is to use Hess's law, right? So if we know this process, we can combine them to find the process that is on top. The process on top is the target, is what we want to find the information about. We use the three equations on the bottom to accomplish this goal. We have to observe how the information is presented. So the first equation here on the bottom of the screen, equation number 1. Well, I see carbon. When I move to the top of the screen, I don't see carbon anywhere. So the first equation has a piece of information that I do not need. I already know that this carbon from the first equation will have to cancel with another carbon somewhere else, because on my final equation I cannot have carbon. Moreover, I noticed that the first equation contains a molecule that I need. It contains CH4, but the CH4 appears as a product, and I want CH4 as a reactant. What is my conclusion upon this observation? In order for me to put the CH4 in the correct position that I need CH4 on the left side. I must flip equation number 1. I flip equation number 1 when I do, the sign of delta H is going to change. When I look at equation number 2, I notice two things. I notice that equation number 2 contains oxygen, and the oxygen is already in the correct placement. But I need 2 moles of oxygen, and I only have 1 on the bottom. So I'm going to keep that information and see if I need to do something later. The second point about equation number 2 is that the molecule of CO2 is in the correct location. Looking at the top equation, CO2 is supposed to be a product, and on equation number 2, CO2 is a product. Moreover, the correct amount is there as well. Top equation, I need 1 mole of CO2. Bottom equation number 2 has 1 mole of CO2. So what is my conclusion? My conclusion is, because of this CO2 business, I am going to keep equation number 2 as has been given to me. I'm not going to change anything. So I am keeping the value of delta H. I'm keeping the equation just like it is. And finally, I look at the third equation. And what do I see on the third equation? I see H2O. And the H2O is in the correct position. So I am going to keep this equation as it is because I have the H2O in the right place. So the next slide, the slide that you're looking at now, the bottom, shows the transformations that have taken place. I'm going to take it back one thing that I said. We do have to multiply this equation by 2. So the oxygen on this equation cancels with the oxygen on the second equation. Adds to the oxygen on the second equation. And eventually 2 moles of hydrogen that we have here is going to cancel with the hydrogen that is on the first equation. There is a typo on the top of this slide. We're supposed to have 2 moles of water here to balance this equation. That's why we need to multiply the third equation by 2. So you will see these transformations. You will see that the first equation has been flipped. You will see that the second equation has been kept the same. And you see that the third equation has been multiplied by 2. Notice that the transformations that took place with the first and third equation were also transformations done to the enthalpy. So once we complete the transformations, what do? We sum the 3 equations. We confirm that we obtain the equation that we wanted to obtain. And we sum the enthalpies after the changes have been implemented. So notice that this sign here changed from negative to positive. And notice that the numerical value of enthalpy for reaction number 3 has been doubled. So summing all these changed enthalpies, we get a value of negative 802.5 kilojoules. So this is still the second methodology of calculating enthalpy. We have a third methodology to calculate enthalpy. Let me fix this coefficient again here. And the third methodology is that equation we saw before. Delta H equals summation, number of moles, standard enthalpy formation for the products, minus summation, number of moles, standard enthalpy of formation for reactants. Your eye has to capture the products minus the reactants here. This slide that you're looking right now is showing that regardless of the methodology you choose to calculate enthalpy, the values must be the same because it's the same equation that we're dealing with. So if you choose to use Hess's law, the combination of the equations that we went over, or if you choose to use this version in front of you of Hess's law, based on the standard enthalpies of formation, the results are going to be the same. So if you could, looking at the screen and following my voice, I'm going to color code this and try to make you comprehend what you're looking at. Let's first focus on the product side of the chemical equation. So looking at the top of the screen, you see CO2 and water. I'm going to change my color. We have 1 mole in green of CO2 here. On the bottom of the screen now, you will see delta H0F of CO2, and there's no number being multiplied by it because it's actually being multiplied by 1. And what is the result? The result is here. From the table, the standard enthalpy formation of CO2 has been identified and written here. Okay, going back to the top of the screen, we have 2 moles of water in red. So, bottom of the screen, 2 moles, standard enthalpy formation of water. So we go to the table and collect this value, 2 moles of the value that we collected. And this completes the product side of the equation. This completes summation. The summation is here. Summation is here. Summation of number of moles, delta H0F for the products. Okay, now let's look at the reactants. Minus the reactants. The reactants are coming out. Changing color to blue. 1 mole of CH4. Bottom of the screen. Delta H0F of CH4. We multiply this by 1. This is the number that we get. From the table, the standard enthalpy formation table. Moving on, in orange, 2 moles of oxygen. So we are here, 2 moles of the standard enthalpy formation of oxygen. And that number is 0. Why? Every pure substance in their standard state has their delta H0F equals 0. So since we're talking about oxygen is an element by itself, not combined with anything. Oxygen in this equation is a diatomic gas, so the standard state is being respected. So therefore, delta H0F is 0. So once we substitute everything into the equation, we of course completed the reactant side. So we completed summation of N delta H0F for the reactants. That concludes everything. Then we can put all these numbers together and find the actual result. So this is the final example for this lecture. Example 711 from the book. Use the standard enthalpies of formation to determine delta H0 of the reaction. Is standard enthalpy of the reaction. For the reaction given is balanced. So the approach the book takes is, it lists the reaction that is given in the problem. It writes down what we need to find as a goal and the conceptual plan to find it, which is this equation of delta H0F. So let's drag using the same colors, going to the product side. 4 moles of NO. 4 moles of NO. Where's this number coming from? From this table. 6 moles of water, 4 moles of ammonia, and 5 moles of oxygen. We have the summation of the products minus the summation of the reactants. Thanks for watching, students.